All right, chemistry peeps. This video is going to be going over types of chemical bonds. So if you're looking at your visible learning document, this is 4-1. So we're going to talk about the three types of chemical bonds. So ionic bonds, covalent bonds, and metallic bonds. When it comes down to metallic bonds, you really just have to know how we define it and kind of how we might depict it a little bit. But other than that, we're probably never going to touch on metallic bonds that much. The main thing is ionic bonds and covalent bonds. And when we talk about covalent bonds, there's a few different ways we want to be able to classify them. So covalent, and then when it's covalent, we have double, single, or triple covalent bonds. And then we also have polar covalent versus non-polar covalent bonds. And then we have this thing called sigma or pi bonds that all fall under the covalent category of chemical bonds. So it's really just ionic, covalent, metallic. But when it comes down to ionic and covalent, covalent again is just another. There's a bunch of different subcategories of a covalent bond that there really aren't in ionic bonds. Okay, so I guess another thing to understand too is a lot of you have heard of the term and maybe learned about it, hopefully, in biology, hydrogen bonds. Like, water has something called hydrogen bonds. Understand that hydrogen bonds or hydrogen bonding is not a chemical bond. Okay, it's a different type of attractive force, but it's not a chemical bond. So when you're doing your bond assessment in Schoology, hydrogen bond's never the answer because that's not a chemical bond. All right, hydrogen bond will be an answer down the road when we get to Unit 5, and we'll talk in detail what a hydrogen bond is. But right now, don't let that be a distractor to you. Hydrogen bonding is not a chemical bond. All right. So again, ionic, covalent, metallic. That's what we want to learn about today. All right. So let's go into it. All right. And before you kind of watch the rest of this video, review this handout. Right. This is the types of bonds review. And it goes over what an ionic bond is, what a metallic bond is, what covalent bonds are. And then once we have covalent bonds, different types of covalent bonds, polar versus nonpolar. And then we have sigma versus pi bonds. And this kind of goes in detail on what those things are. All right. But check that out. That'll help you out. All right. Let's go into our lesson today. All right. So chemical. Remember, when we talked about chemical versus physical changes, the word chemical means it involves electrons. So we're talking about losing electrons, we're talking about gaining electrons, we're talking about sharing electrons. Any chemical bond is made by either the transfer or the sharing of electrons. That's what's going on. It's got to involve electrons somehow, all right? So let's understand that, right? Hydrogen bonding does not involve the electrons being transferred or moving around or anything like that. So that's why hydrogen bonding is not a chemical bond. All right. So the types of chemical bonds we want to look into are ionic, covalent, metallic. Okay. Now, just again, for covalent, there's a lot of different subcategories we want to be able to describe them. So covalent bonds can be polar or nonpolar. They can also be identified as sigma or pi. Okay. And they also can be single, double, or triple. And I'll get into that in a second. All right. And again, hydrogen bonds are not chemical bonds. Hydrogen bonds are not chemical bonds. Okay, hydrogen bonds are what we call IMFs. They're intermolecular forces. All right, they're different than a bond when we think about bonds in a compound. A hydrogen bond is interactions between molecules, not within a molecule. All right, so again, these are the three main types. We want to be able to classify covalent bonds a few different ways, and essentially we just need to know the definition of a metallic bond, okay? So let's dive into that. All right, so first, ionic bond. All right, the first type of compound we're going to be naming and writing the formulas for are ionic compounds. So let's talk about what an ionic bond is. It should make sense to you that ionic compounds have ionic bonds. Okay, great. Now, What is an ionic bond? A lot of times we use the keyword transfer to explain what ionic bonds are. You can say the transfer of electrons or the exchange of electrons. One thing losing electrons, another thing gaining electrons, right? That's what an ionic bond is. Now, technically, an ionic bond isn't the transfer of electrons. It's not the fact that sodium gives an electron to chlorine. That's not what an ionic bond is. The ionic bond is the result of the transfer. So a lot of times we just say ionic bond, ionic means transfer electrons, covalent means sharing electrons, but really the ionic bond is the result that electrons have been exchanged. Okay, so I'll show you what I mean by that. All right, so calcium is a metal with two valence electrons. Metals want to lose those valence electrons. So calcium wants to lose two. Oxygen is a non-metal that has six valence electrons, but it would like to have eight, so it needs to gain two. All right, so we'll transfer the electrons. The two electrons from calcium will transfer over to the oxygen, okay? But understand that's not what the bond is. After the transfer occurs, understand what we have now. Now we have a calcium that has a 2+ charge. We have oxygen or oxide now with a 2- charge. And the reason why they're bonded together now isn't because the electrons have been transferred. It's the result of that transfer is this particle is now a +2, this particle is now a -2, and we know opposite charges attract. That's called the electrostatic force, right? And so what's binding them together? The electrostatic force. So the electrostatic force or Coulombic attraction is basically the same thing. That is what an ionic bond is, okay? Positive ion and a negative ion attracted to each other, bonded to each other because they transferred electrons from one thing to another. And after the transfer occurs, now something's positive, something's negative, and they're attracted to each other through opposite charges. Okay? So the attraction that forms from the result of the transfer of electrons, that's what the ionic bond is. Okay? Okay? But a lot of times we'll simplify it and just say, hey, ionic is transfer or exchange electrons, and covalent means share. Okay? I'm going to finish with covalent because that's the one with a lot of different categories. So from ionic, I want to go to metallic and just talk about the basic definition. All right. So metallic bond, right? You're going to find these in metals. So this isn't going to be found in necessarily compounds. They're going to be, metal elements. So like this is going on in gold or copper, just the element itself, or it could be an alloy, which is kind of a mixture of different metals, like brass and stuff like that. Same idea. But in a metal structure, all right, the valence electrons of a metal, and it's not just the valence electrons, a lot of the d electrons that these metals have are free to move. All right. So the way we describe a metallic bond is a sea of valence electrons. Now, really, what that means is they're delocalized. Okay. What does that mean? It means the electrons, especially the outermost electrons of the metals, the highest s and the highest d electrons, are free to move from one nucleus to another nucleus. They're not stuck around one nucleus. They're allowed to bump from one atom to another atom to another atom within the structure. They're delocalized. They're not local to one atom. So because they're free to move, okay, that's the reason why metals are good conductors of electricity. So if you ever, like all those properties of metals that we talked about in Unit 3, good conductors of electricity, good conductors of heat, good conductors, they're malleable, they're ductile. All those properties of most metals is due to the fact that they have delocalized electrons. So why are metals good conductors of electricity? Because of metallic bonding. Why are metals ductile or malleable? Because of metallic bonding. Okay, so the definition is delocalized or sea of valence electrons. A sea kind of implies that, they're not just in one place. They can move from atom to atom. Okay. But the main thing to take from this is because whenever you have electrons that are delocalized, you have something that has the potential of conducting electricity. Because all electricity is the movement of electrons across a medium. So think of a copper wire as a bunch of copper atoms lined up. Well, the electrons are free to move from one atom to other atom within that wire, and that is electricity conducting. That's what it is. All right. Now, the other thing I want you to take from this is how we depict metallic bonds. It's pretty simple. Let me show you here. Okay. So this is how metallic bonds are kind of shown. So you have like what the positive spheres next to each other represent. This isn't an ionic structure because ionic it would be positive, negative, positive, negative, positive, negative. This is just a bunch of metal nuclei next to each other, and then these tiny red dots are supposed to represent the electrons. And notice that they're not kind of uniform within the structure. They can go pretty much anywhere within the structure. Okay, so this shows metallic bonding. This shows metallic bonding. This is another way to show metallic bonding. Okay, so that's really all you need to take from that. It's not something that comes up a lot. Just, there are things that we call metallic bonding. All right, and that's when the electrons are delocalized or free to move. Okay. All right, so back to this. Now let's get into covalent. All right. So when nonmetals react with each other chemically, they share electrons, right? So metals lose, nonmetals gain, but really nonmetals gain when they are paired up with a metal, because the metal will lose electrons to the nonmetal. But if you have two nonmetals that want to try to satisfy the octet rule, right? Right? Nonmetals don't want to lose the electrons they already have. They just want to gain more electrons. So when you have two things that just want to gain electrons, then instead of one losing and one gaining, what they'll end up doing is sharing electrons. Okay. So a couple things here. When two atoms share two electrons, that's called a single bond. When they share four electrons, that's called a double bond. And when they share 6 electrons, that's called a triple bond. It would be a single covalent bond, a double covalent bond, a triple covalent bond. Okay. So how does a single bond form? Well, if we look at hydrogen and fluorine, fluorine has 7 valence electrons, so it has one dot, one electron not paired. Hydrogen has 1 valence electron, and so that's 1 electron not paired. When the electrons aren't paired, that's when they start to free up to bond. So hydrogen's coming in and saying, hey, I got 1 electron. Fluorine's over here, I got 1 electron. Let's put them together. Let's put them in the middle between us, and we'll share them. Those 2 electrons will belong to me and belong to you. So that's what they do. So one way to show it is like this. 2 dots between 2 atoms is a single covalent bond. But a lot of times we'll draw it like this, a dash. A dash means 2 dots, 2 electrons being shared. Right? That's what's going on there. So that's a single covalent bond. Now, when they're being shared, those 2 electrons count for both atoms. So right now, in this structure, hydrogen has 2 valence electrons, the same as helium, its closest noble gas, and fluorine has 2, 4, 6, 8 valence electrons. So the same number of valence electrons as neon, its closest noble gas, right? So we're satisfying the octet rule. That's why these bonds are being formed, okay? So how does a double bond form? Well, if we look at oxygen, O2 is a molecule with a double bond, and it's because each oxygen has 6 valence electrons. So if you draw its dot structure, this oxygen has 2 unpaired electrons, this oxygen has 2 unpaired electrons. So you get 1 bond, 2 bonds, you get a double covalent bond. So that represents 4 electrons being shared. So this oxygen has 2, 4, 6, 8 electrons. This oxygen over here has 2, 4, 6, 8 electrons. Because again, when they're being shared, they count both ways, right? So that would be a double covalent bond. Okay, well, how about a triple? Well, nitrogen is a diatomic molecule with a triple bond. All right, because nitrogen has 5 valence electrons, 5 dots around it. 3 of them are unpaired, so you get 1 bond, 2 bond, 3 bond. You get that triple bond, and now nitrogen's satisfying the octet rule because you got 2, 4, 6, 8 for that nitrogen, and you got 2, 4, 6, 8 for that nitrogen. Okay. All right. Also, with covalent bonds, we have to worry about this thing called polarity. Are they polar or are they non-polar? Okay. Polar still a polar bond is still a covalent bond, so the electrons are being shared. A non-polar bond is still a covalent bond, so the electrons are being shared. And it's really just how well do they share? That's really what it comes down to. Okay? A polar covalent bond is unequal sharing of electrons due to electronegativity difference. So if you remember, electronegativity is the ability the atom has to pull electrons to it. So when you have two things sharing electrons, they're throwing their electrons in the middle and they're both holding on to them. Well, if one of those atoms is more electronegative, it's actually going to be able to pull those electrons closer to it and further away from the other atom that has a lower electronegativity. So what that does is it creates opposite charge sides to the bonds. And when you have opposite charge sides to anything, that means that thing is polar. Okay? So a polar bond is just a bond where one side of the bond is negative and one side of the bond is positive. And the reason that happens is due to electronegativity difference between the atoms in the bond. So if we look at this HF bond, yes, it's covalent, they're sharing the electrons, but they're not sharing them equally. How do I know? Well, I know fluorine is the most electronegative element. Fluorine is much more electronegative than hydrogen. So they're not really sharing them 100%. So most of the time, those electrons in the bond are hanging around this atom. So this atom starts to gain a positive charge, or sorry, a negative charge, sorry, because it has more electrons around it. And as those electrons get pulled away from this nucleus, this becomes positive charge. This symbol right here just means a partial negative and a partial positive. It's not a full negative one and a full positive one because it's not ionic. There's not a full transfer of electrons. What it is an unequal sharing. So the more electronegative element is going to get the negative dipole. The less electronegative element is going to get the positive dipole. That's what we call these opposite poles. And that's what polar means. You have opposite dipoles, a negative dipole and a positive dipole. So this bond is polar because this side of the bond's negative and this side of the bond's positive. But the reason that happens is because of the electronegativity difference between these two atoms that are sharing the electrons. Okay? So HF is a polar covalent bond. How do I know? Well, they're two different atoms, so they have two different electronegativities. Now, you have to go back and remember your electronegativity trend because the bigger the difference in electronegativity, the more polar the bond. Okay? And you have to know which of the two atoms, which one is more electronegative, because that'll tell you where the negative side is versus the positive side of the bond. All right. So what is nonpolar covalent? That's when the electrons are shared equally. All right. And that's true, especially when you have a diatomic element, right? There's zero electronegativity difference between this oxygen and that oxygen. They have the same because they're the same element. So these 4 electrons that are being shared here, right? A double bond, 4 electrons, 2 dots and 2 dots. They're being shared equally because there is zero electronegativity difference. So you don't get a negative side and you don't get a positive side. So this is a non-polar bond. Or another way to say it is 100% covalent. 100% covalent means equal sharing. Okay? All right. So here are 3 polar bonds. I know that this is the negative side of this bond because I know nitrogen is more electronegative than hydrogen. I know for this bond, this is the negative side of the bond because oxygen is more electronegative than hydrogen. And I know that this is the negative side of this bond because I know fluorine is more electronegative. Now, they're all polar bonds, but of these polar bonds, this would be the most polar, HF, because there's the biggest difference in electronegativity here. And this would be the least polar because this is the least difference in electronegativity. They're all polar, but their difference in polarity based on how different the electronegativities are. So the bigger the difference in electronegativity between the atoms in the bond, the more polar the bond. Okay? So the larger the difference in electronegativity, the more polar the bond. All right? And I'm just showing a bunch of single bonds here, but you could have a double bond that's polar. You could have a triple bond that's polar. As long as the atoms that are bonded to each other are different, then it's going to be polar. How polar depends on how big a difference in electronegativity there is between the atoms in the bond. All right. All right. Now let's talk. The last part of covalent bonding is whether it's sigma or pi. Now I'm just going to give you the straightforward, this is what you need to know. And if you want to know more, again, I'd reference this. Go to the types of bond review and go to the back. This explains exactly what a sigma bond is. This explains exactly what a pi bond is. And if you have more questions, you can Google it or you can come ask me after school. But right now, we're just going to focus on what you need to be able to do. All right. So here's the deal. Every single bond is a sigma bond. So one single bond is one sigma bond. Okay? A double bond is one sigma and one pi. One of the bonds in a double bond is a sigma. The other bond in a double bond is a pi. Okay? A triple bond is one sigma and two pi's. So when you have a triple bond, one of those bonds is a sigma bond, but the other two bonds are called pi bonds. And that's really all you need to do, is be able to look at a structure and count how many sigmas there are and how many pi's there are. Okay? So understand, you only get pi bonds once you have a double or a triple bond. If all you have are single bonds, then all you have are sigma bonds. Okay? So in this structure, I want to know how many sigmas and how many pi's. So really, you just count the total number of bonds. 1, 2, 3, 4, 5. 5 total bonds. It doesn't matter if it's double or triple. 5 total bonds. That means 5 sigma bonds. And then if you have a double bond, then that one of the bonds is sigma, the other bond is pi. So in this structure, we have 5 total bonds, so 5 sigma bonds, and then we also have 1 pi bond because we have a double bond. Okay? And then in this structure, if we wanted to count how many sigma and pi's we have 1, 2, 3 bonds, so that's 3 sigmas. And then a triple bond contains 2 pi's, so we also have 2 pi's. Right? And so when it comes to identifying sigma and pi bonds, that's basically all you need to be able to do. All right? So knowing this right here, that's what you need. Okay? All right. So hopefully that helps you. And now doing that 4-1 Schoology assessment, types of bonds, that should be a breeze. But yeah, ionic, covalent, metallic. Then with covalent, polar versus nonpolar, single versus double versus triple, sigma versus pi. And then just remember, hydrogen bonds, not a chemical bond, right? Hydrogen bonds, not a chemical bond. So ionic, covalent, metallic. All right. All right.